Hey class, I hope your first week back from the break is going well. Well, let's, in keeping with a running theme for this course and every course that I teach, uh, I will be presenting material that I was almost fully prepared for. It's a review of some of the material that I generated for this course last semester, in terms of background knowledge and everything, for computer science and discrete math in general. But in preparing for what I hope to be material for a future lecture, I I didn't review this as much as I had wanted to. So don't worry, I know it. I generated it, so it's fine. But I apologize if the presentation is lacking in showmanship in any way. Okay, so let's jump into it. Okay, so uh, I know that you all come from different levels of background. Some of you may have focused more on math, in high school and so far at UTD. Um, some of you may have focused more on programming. Some of you may have focused on mainly on getting the required coursework out of the way, and you haven't had much of a chance to do anything in CS or math. So, if that's the case, then I felt like it would be prudent to develop some common ground so we can all, uh, you know, uh, build up from some common base of knowledge. In the spirit of that, I wanted to talk about some of the main concepts that we're going to look at. So, data structures, for one. Algorithms and data structures is its own course, but that doesn't mean that we can't encounter it before we study them in finer detail. And then some basic knowledge of operating systems and how they work, and then kind of an introduction into programming. Since I'm going to be presenting a lot of code, I think it's important that we start to develop a common way of discussing it. Uh, and it's a little less give and take than I would like in a traditional classroom setting. So it feels a bit dictatorial and like, well, this is how I talk about it, and you can't really, give me the level of feedback you might be used to with an in-person setting. So it's just the way it's going to be. So I do apologize for that, but hopefully, my manner of speaking about programming is found acceptable. And then whatever other material I'd stuck in section 9. So we'll go right into it. Okay, so data structures are the complement to the primitive data types that are provided by every programming language. So the modern languages will provide string and bool, but if you're looking at languages like C that are a little older, a little more experienced, then they're only going to provide fewer data types. They'll provide an int, they'll provide a float, they'll provide a double, they'll provide a definition for something called a struct, which allows you to create a complex data type with these others. And then they'll provide pointers for int, float, double, char, which is a single byte integer. And so, you think of a character, then you think of letters that you might type, and that's kind of its own thing as soon as you start discussing the encoding types that you would look at and so forth. But the primitive way to represent a letter is to actually represent it as a number, which is 8 bits, a single byte, and the values range from 0 to 255. So the Ascii system, which is basically all you're going to look at whenever you're an undergrad student, and it's a little bit unfortunate because as soon as you get into the professional world, you're going to move to UTF-8 or some other encoding type where there's not one character to one byte correspondence, and then you'll have to figure it all out on your own. So So that's something for you to look forward to. But we'll discuss encoding types a bit. Not in a terrible amount of detail, but we will at least introduce you to the concept. But for now, whenever we discuss strings, we can consider them as a collection of single byte characters, and rather than using the numeric interpretation of a character as being an 8-bit number, we'll refer to it as letters and numbers and printable characters, and we'll mention that there's non-printable characters as well. That'll come up. But a string, whenever you're in C, is actually a pointer to a character array. It's a character pointer. And that caused all sorts of issues in terms of security. So, you'll go over it a little bit, but if you have time and you're curious, look up buffer overflow or buffer overrun or whatever errors in C, and you'll understand why strings were changed to be their own primitive data type, and they are an immutable data type in the languages that implement them, meaning that if you add a single character to it, so if you have a paragraph, or if you have a string that's the size of this document that's potentially thousands of characters long, adding a single character doesn't add a character to it. It creates an entirely new copy, which is in this case, 1 byte longer, and it appends that, so now you have 2 copies. So building up these strings by tacking on a single character is something that is going to be unexpectedly expensive, and so you'll have to learn to use certain data structures like string builder, which will help you get around this problem of using just a monstrous amount of memory and computer resources to add a single character to a string here and there. But anyway, I don't want to talk about string manipulation the whole time. Well, it'll get its fair share. But for now, what I want to talk about is just the more complex data structure. So I said that strings they're an address in memory. So you can think of character pointers or integer pointers or struct pointers or whatever as being kind of like a lookup in the index of a book. So it doesn't tell you what it is, it tells you where to go to get the definition of that thing. So it's on page 25, and then you'll have to browse page 25 to figure out where it is in memory. Although in computer parlance, the pointer it takes you right to where you need to go, so it's more accurate than just saying it's on page 25. It's more like it's on page 25, paragraph 2, the third word in the second sentence. Like it's exactly where you need to go. Okay. So what is a struct? What is a class? What are these complex data types that we might actually look at? And then are there, well, I won't ask you the question that I'm about to answer. There are additional types of structs or data structures that are more than just this generic, or that are more than just a specific class of data. They deal with certain solutions to well-known problems, and we'll look at them in a little bit. They're linked lists and heaps and these patterns of housing data, of storing your data based on how you intend to use it. But first we'll deal with the introduction to this, and that's okay, so I have a collection of data that's all related. So I want to be able to store a student in memory so that I can have a collection of students, and I can generate some sort of reports, or I can look something up or change something very specifically, or I can create trends. I realize that GPA has been on a downward slope based on this event in time or whatever, right? You need to be able to store it in memory so that you can start to ask questions against the data, and so as you practice, you'll develop certain patterns to do that. But the overall trend that you're going to deal with is you have a data type, and then you have a name for a field, and then the struct is the umbrella. It's the manila folder, if you want, that houses all of these individual bits of data that should be gathered together. And then a class was an improvement on the struct, which allowed you to both identify data that should be grouped together, such as student data, and it also allowed you to define these class methods, these functions, that will act to manipulate the data, or it'll act to generate a string. So like if I have a student and I want to know the student's name, well, I don't want to have to print out their first name and then their last name, or last name, comma, first name, space, middle initial. I want a convenience method where I just have like print name, or name, and then you give me a string, or like get name or generate name, whatever, and then you give me the string, and then I print that string. But I don't want to have to do the work everywhere that I might want to access it. I want something that's a little bit reusable. And so those reusable utility methods, along with methods that will actually change the data, those should all live in the same class, and in this case a student class, and they live in the same file. It's easy to identify any errors. You only have to go one place to fix an error with the method, instead of potentially hundreds or thousands of other locations in the code. Trust me, if you do not follow good programming practices, it very quickly gets out of hand, and it essentially becomes such a sprawling problem that you can't fix anything in it. So you don't want to get there, right? Maintainable code is what we trade in as software developers. So good programming practices are important to identify and then keep in practice. Okay, so that's enough about the motivation for structs and then classes, which are structured data with methods acting on them. Okay, so a linked list is a particular type of data structure, and it defines a chain. So you can think of it sort of as a scavenger hunt, right? So you're told to go to one place first, and then whenever you get there, the note or whatever it is that you find at that location will tell you where to go next. And then whenever you finally reach the end of the scavenger hunt, that note will let you know that there is no next step, right? This was it. This was the final link in the chain. And so, it's efficient and flexible in that you don't need this big contiguous block of memory in order to move from one location to the next. But it's inefficient in that everything is a scavenger hunt, right? Like, okay, if you need your socks to get dressed in the morning, you don't want a scavenger hunt to find them. You want them to be in this one easily located position, right? I want to go to wherever the socks are. I don't want to have to hunt them down. So the advantage of linked lists is the flexibility, and that you don't have to know how much data you're going to be storing up front. You can arbitrarily grow and shrink the list as you want. But the disadvantage is that you can't, without the assistance of some other data structure, you can't readily access things in a single go. And we'll talk about hash maps in a minute, which do provide you with the ability to find your socks, right? But okay, so an example of where linked lists are used in current programming practices is as a chain of events. So whenever you have an event handler, or an event is typically just something that a program can't anticipate, like when a user presses a key. That's an event. So no operating system in the world or program should know what button the user or what key the user is going to press next, or where on the screen their mouse will click. You wait for the event to happen and then you react to it. And so the way browsers are set up, if you click on a position in a browser, they have this stack of objects that all are, where potentially many objects are on that web page, on that position on the screen presented by the web page. And you have to figure out what the user is actually clicking on. Are they clicking on the document body? Are they clicking on a button that's at that position? Are they right-clicking? Are they, what are they doing? And so as you build up your web page, or whatever, this is true of desktop applications as well. As you build it up, you are creating these objects, and they have a presentation, and then they have a collection of things that happen whenever something happens to that presentation. And so if you want to respond to an event, then you subscribe to an event handler, or you subscribe to the event chain. So you say, okay, well, if the user clicks on this thingy that I've created and placed here, then I want you to call this method, this function that I'm giving you right now, and that function will know what to do. And so, but because these objects live on top of each other, sometimes they're hidden, sometimes they're, or usually they'll be visible. But you want to be able to react, in whatever manner you say it should act. And so you subscribe to this chain, and then everything that is subscribed will get called, but it'll get called in a linked list manner in the event of a chain. So whoever was the first to subscribe will get a shot at handling it, and then, or it might be the reverse order. It might be the last to subscribe actually gets the chance first. And so then that method gets called, and whenever it returns, the next method in the chain will get called, and so forth and so forth. But you can interrupt it typically by calling prevent default. So imagine that a key is pressed inside of a text box or an HTML input element. So someone is typing their name, and their name is Charlie. Well, Charlie has a C in it. So usually you would want that C to be printed whenever they press that button. But what happens if it's Control C? So they've highlighted some text and they press C when it's in combination with Control. Well, in that case, you don't want the default behavior, which is to add a C to that position. You want to prevent the default behavior and then perform some special action like copying it to a clipboard, which is provided by the operating system, and so forth. So the linked list gives you that flexibility of waiting until some event happens and then responding to it based on a system of rules that you present. And then if necessary, to interrupt the scavenger hunt, to say, oh, no, if I sent you to the park and it turns out that there's a fire there, or whatever, then the scavenger hunt's off. You shouldn't go any further, right? Okay. So then, so just some terminology that you'll see used with linked lists, and basically in several of the data structures that we're going to deal with is a node. And so before I went to UTD, I'd never heard of a node. I didn't know what it was. Obviously it had existed, I was just unaware of it. And a node is just a thing, right? It's it's just a point in space, or it's it's the word that we use to represent the concept of a thing, right? So whenever we're dealing with these trees or linked lists or graphs or whatever, then whenever we draw them on a whiteboard, it'll be a point, and then they'll be connected by these lines or arrows or whatever. And so the point, it's sometimes we'll call it a vertex, sometimes we'll call it a node. but it's whatever concept we're discussing. It's just a placeholder, just like the word thing, right? But it has a very specific context in that, usually whenever we're talking about a node, it's dealing something to do with the computer sciencey concept, right? So in terms of a computer network connected by a router or a switch or a hub, the nodes are the things that the cables plug into, or the things with wireless devices that allow them to communicate with each other. So a node can be a desktop computer, it can be a laptop, it can be a cell phone, it can be the router. It's just a thing, and then the context is derived from whatever you're discussing. So in the case of a linked list, a node is just the next link in that chain, or the next note in the scavenger hunt. Okay, so a singly linked list has a head, so you have a starting point, and if it's null, then there is no scavenger hunt today, right? Or if it's not null, then it's that first thing, and then it'll tell you where to go from there. A doubly linked list lets you go from, it lets you start at the beginning or at the end and then work your way backwards. Or you could start at the beginning and work your way halfway through the list and then work your way back to previous elements. But however it's defined, there's workarounds for all of it if you need something that isn't provided. So here's an example of a doubly linked list. So it's written in C, which some of you will be familiar with. Probably about a half or 2/3 of you will not. But just bear down, right? I'm not asking you to compile it or link it or anything. Just try and familiarize yourself with the flow. We'll go through examples in C. We'll go through examples in Java, JavaScript, C#, Python. So just focus on the overall form of the code and not so much on the details, and you'll be fine. Okay, so the star is declaring a pointer, right? So I said that this points you to the first character in a string whenever you're dealing with C. This is a node pointer, so you can declare something to be of a type within itself, right? So we're defining a node here, and then we have references to other nodes, which makes sense, right? So if we're defining our scavenger hunt, right, if that's our type of linked list, then we have a note, and in it will have a reference to the next node, right? So it looks a little weird at first, but it starts to make sense over time. Okay, so it has a name, it has a next, it has a previous. The double list has a head and tail as promised, and then we have this method. So C does not define classes. So whenever we define our functions, they have to accept the type, where if it was a class, it would be this dot append, but here we accept the type that it's going to act on, and then whatever parameter it needs in order to perform the action. So we take in a list, we look at the head. If the head is null, then the list is empty. So we're appending, we're doing a little more than appending in this case. We're actually creating the new head. So if it's equal to null, then the head is this new tail, and the tail is also the tail. In every other case, if there's already a list and we're just looking to add something to the end of the list, we modify the new tail to have a previous node of what was the last element before this new one came along, and then and then vice versa. So we go to that element and we make it aware of this new element, and then we modify the list itself and say, okay, so this new element that was passed in is actually your new tail. Right? So that's what an append method looks like. It's you'll see patterns like this whenever we're replacing these values of variables, and it never makes sense at first. But if you program enough, and it'll probably take, I don't want to put a big number out there to discourage you from doing it, but honestly, it'll take at least a couple of hours of struggle. Not all at first. You'll be able to do it, and then you'll forget it, and then you'll do it wrong again, and then you'll forget it again, and then, after you've done it, maybe a dozen times, maybe fewer if you're a quick study, then you'll get a feel for the pattern. But if you don't code for a while, then you'll lose it quickly. So just a warning. But yeah, so it looks weird, the order of events, but it is well defined. And so another time that you'll see some strange looking orderings like this is whenever we perform a swap within an array, or we try and replace two variables, or try and change the value of two variables, swapping the value of the two. Anyway, we'll get to those whenever we deal with sorting. Okay, so and then this is our main method, which kind of sets up the thing. So we have a pointer to our doubly linked list. This is the name of our variable. We declare that it is a struct. Here we say that it's a struct of this type, so it's going to be a pointer to a double list instance. We politely ask the operating system to allocate a block of memory, which is the size of all of the variables included in our struct. And the size of operator is able to look at this and says, okay, well, a character pointer is just whatever the length of a word is in your operating system. So if it's a 32-bit machine, then this is 4 bytes. If it's a 64-bit addressed machine, then it's going to be 8 bytes. Again, a memory address is going to be whatever the size of a word is. Again, a memory address is going to be whatever the size of a word is. So 32-bit, this is 4 bytes. 64 bits, it's 8 bytes. Okay, so we politely asked for our memory allocation, and then we've taken what was returned and we cast it as a doubly linked list, and we've stored it in our list variable. And so now we want to start initializing values. So the head is null and the tail is null by default. Then for the purposes of a demonstration, we create a first node and a second node and so forth. And so this process is exactly the same. So I've defined this abstract concept of a node. I want to politely ask the operating system to allocate a block of memory, which is the size of all of the pointers and variables I have declared in my struct of type node, and I want you to cast that block of memory as this type and store it in this variable. Alright. Okay, and then once I start assigning values, first name, so the name value within this block of memory that represents my node for my first node, and then just indicating that characters are constant strings are character pointer types, and then the next node is null, previous is null. I call append, I pass it the list that it will be appending to, and then the node that I want appended to that list, and then it'll update these values. Right? We defined it up here. It'll go in and update them as appropriate, right? So for the first node, the head was null before we passed it in, so it's going to execute this and then return, and then next and previous are going to stay null, right? So in this case, I want these to be null. So if I wanted this to be maintainable, I would extract this process of creating a node, and I would create a new method which always initializes next and previous to null, does the work of allocating the memory, and then it accepts just a character pointer for the name strings that it'll perform this assignment. And whenever you deal with Java and C# and Python and almost any other modern programming language, you'll have a new operator, which actually does this polite request for memory and size of action, and then the casting as well. Right? So it does all of that. So it would just be new and then node, right? And it would call the constructor, and you could pass this into the constructor. That pattern, this pattern of creating a block of memory and then assigning it, casting it to a particular type, and then assigning it or whatever, is so familiar, and even initialization, that the newer programming languages, C++, Java, C#, they all define this new operator, and then it allows you to define a constructor to do exactly this. So that you can set it up and it's all done in some location instead of having to copy the same code over and over again. Because the more times you copy code, the more chances there are to introduce a bug into the program. And debugging is no fun, especially in the older languages when the debuggers weren't as good. Anyway, okay, so we do the same thing. We create another node, right? We create a second node. Somehow I messed this up. Okay, well, obviously this line should be down here. Knock on me for not running my code. I should have shown up. Anyway, so this line actually below this, and then again the initialization. So you see how easy it is to mess it up. Well, whatever. Okay, so if it were to work, then we would append that second node to the list, and then we could do whatever we want with the list. And then in C, you should always, you're managing your memory. You're managing your own memory. So ideally, we would define more than an append. We would define a remove, which removes the node from the list. And then once the node is no longer required, we should free it, and so forth. And so, if you're saying, okay, well, I have to keep track of my own memory, and then I have to tell the operating system when I'm done with it so that it can reclaim that block of memory, a reasonable question is to ask is, how am I supposed to keep track of all of these things that I'm creating? And that's where heaps come in. And in fact, it was such a problem and so easy to mess it up that's what modern frameworks do for you. So in C++, you still have to manage it. But in Java and C#, it's managed code, so the heap is maintained for you. And once an object or an instance of a class is no longer reachable by code, it keeps a reference counter. And once there are 0 references to it, except by other unreachable code, then it reclaims it for you. And so that's what's known as managed code. And it's really nice for new programmers. So you can write something, you can get to the point where you're writing good code and you're not spending hours or weeks hunting down these memory leaks that makes your good code completely unusable because there was some instance, something was creating some instance of an object and it wasn't remembering to free it at the end. Right? And then you don't have to write your own memory heap and garbage collector. So it's really nice to have that. Okay, so then queues. Well, a queue, the example I give here is like a line in a supermarket, or if you come from other English-speaking countries, a queue is a queue in a supermarket, and the methods that we'll define in terms of methods that act on a queue are enqueue and dequeue. So enqueue is getting in at the end of the line in the grocery market, in the supermarket, and dequeue is whatever you check out from the line. So it's another term for it is FILO, or first in, last out, FILO. So the first one in the checkout queue is going to be the first one to check out, and the last one in is going to be the last one to check out. And so whenever you're kind of dealing with things as they come, then this is definitely the structure that you want to use. But the complement to this is stacks, and that's last in, first out. And so you can think of this as like a pile of plates. And so if you have a stack of plates, then whenever you're unloading the dishwasher, unless you really want to go through the trouble of making it into a queue, you're just stacking them one on top of another, and then whenever you go to make your nachos or whatever other gourmet food you're making, you take from the top, right? So whatever one was the last one placed on top of the stack is the first one to come off. And so functions follow the pattern of a call stack. So if you have a main method and it calls something, and that something calls another thing, and so on and so forth. Well, if the main method exits, and the main was the very first thing executed, then your program's done. Your program has returned, and the operating system is going to reclaim everything. So you don't want first in, first out whenever you're dealing with function calls. So you want to use stacks, where you call a thing and then you wait for it to finish doing whatever it has to do, and then it returns and it gives you some answer to a question, or some change has been done on a particular piece of data or whatever. And so it's done in this complementary fashion, where the most recent thing to be enacted is the first thing to complete. All right. And so the methods that are defined for stacks are push and pop. So enqueue and dequeue for queues, and push and pop whenever you're pushing a plate onto the stack and popping one off for nachos. Okay. So then hash tables, dictionaries, and maps. These are all synonyms for one another. And so whenever we're talking about linked lists being a scavenger hunt and not really solving the problem of telling you where to find your socks, or where the sock drawer is, hash tables, dictionaries, and maps are really what you're looking for. So you have an object called where are my things, and then you pass in socks, right? You look for that, and then it crunches the string socks, and it goes, oh, okay, I know exactly where your socks are, and then it returns you your sock drawer, or whatever, right? And so it's another name for it is a lookup, and so the idea, we'll talk about arrays, and again, if you're not terribly familiar with programming, then arrays are a bit of a different concept as well. So arrays are kind of like high school lockers, if you want to think about them. It's the same amount of storage space, and it's done in this very serial fashion, where the space one right after another, it's the exact same amount of storage capacity, and it's all of the same type, and you put student stuff in there, right? And student stuff may include backpack, it may include gym stuff, it may include books, it may include notebooks, and so forth, right? But it's the same amount of storage space, so it's very easy to allocate and predict how many of whatever you have can go in there, and you can look it up very readily by knowing what locker number you have, right? And that's exactly the address or the index within an array. It's just your locker number for whatever item you're storing. But hash tables and dictionaries and maps, they provide an abstraction on that concept. So not everything has a serial number, right? So I don't want to have to remember the serial number associated with the concept of socks when I'm looking for my sock drawer, right? I want to be able to pass in a string value or something else that will then tell me where it is. And the flip side is, even if you did do the serial number approach, well, what if socks were number like 9,500,000 whatever? Does that mean that you have to have 9 million other array entries or allocations or lockers in order to just have a sock drawer, right? Shouldn't you be able to compose this in whatever manner you want, taking only what's needed? And so whenever you have something that's a problem of that sort, where it's not necessarily just this serialized storage thing, it's composed of these things that are added as needed with these keywords that you can use to look them up, or these serial numbers that are, or an ID number rather than a serial number, which is used to look the thing up. Then really the data structure you're looking for is going to be you can call it a lookup table or a hash table or a dictionary or a map. It's all basically the same thing, but it's the structure that solves that problem, where I'm composing something and I'm going to need to be able to look it up based on some key, and then you give me the value associated with that. And so it's also, for that reason, it's also a key value map. Right? Okay, so in order to do that, then you're going from having a locker number, where you take this number and you go to that specific address, to something that takes an input and it crunches it, and then it tells you where what locker to go to based on that knowledge. So it's this crunching function or this hashing function. And so you take a string, and then maybe you perform some XOR operations on the bytes or something, and then you XOR that against something else. And then you get this this specific location based on that. And so these data types, which you'll probably, except whenever you take algorithms and data structures, you probably won't create your own hash table or dictionary or whatever ever. It'll be provided to you by whatever programming language you're using. But it's important to study it and understand what's going on and so forth. But the implementations that these use, which are hidden from the user, is typically to create an array, a storage array, or an array of pointers or whatever, and then to have this hashing function. And whenever you insert or you assign something to you assign a value for a given key so that you can look it up later, it has this crunching thing that if the under the hoods array is like 100 slots or whatever, or, storage buckets or whatever you want to call them, then it'll perform this crunching action, and it'll give you one of those 100 slots. And ideally, it won't be in serial fashion or some easily predictable fashion. That way, you don't have to deal with what are called collisions or things that slow down the algorithm. Anyway, so it'll take it, it'll hash it up, and then it'll look at the tea leaves or whatever. It'll tell you exactly where to go, and it's super efficient. It usually has an average performance of constant time, so it's just however long it takes to hash it, and then you're there. You're not having to go on the scavenger hunt, and so these are very, very useful tools. And so most of the time, whenever you're looking for something, this is kind of what you're looking for. But arrays, you tend to know when an array is what you actually want. Right? So if you're reading in data from a file, you want an array because the data is coming in, it's ordered, you're going to want to view it in the order that it was stored on disk and so forth. So you very much want an array in that instance. But when you're mixing and matching data and you want to be able to look it up, this is what you're looking for. Okay. And then I give this other explanation as to kind of another way to look at hashing functions, but you can read that if you're interested. Okay, so trees and heaps. So a heap is a very special type of tree. It's a balanced tree. And so it's either a min heap or a max heap. And you have these nodes, so these things, these whatever, and they'll have some property that allows you to sort on, right? So the priority queue or the min heap or whatever. The example that is usually given is whenever you're doing triage in an emergency room. So the nodes are the people that have come in looking for medical help, and then the comparison function, the objective function, it essentially compares how long the person has to live without medical care, right? Without intervention. And so the person with the shortest amount of time to live without seeing a doctor is going to be the one that gets priority, and then everyone else kind of settles in after them, right? So you have this sorted order, right? You come in with your sore throat and swollen eyes, and you're next in line, and maybe there's 15 people behind you, but someone else comes in and maybe they've had an arm and a leg fall off. Then even though you've been there longer, it is still a queue in the sense that there is a next up, but it's a queue where you can kind of jump to the front if you have the greatest priority in that case. And so trees. I mentioned that it's a heap, and the way we've discussed queues so far, a heap is a type of priority queue, is that it's a bit like a line, so there's this serial nature to it. And that's true, but the way that it's stored and the way that it's managed is it's a tree with these special additional properties. I'll just mention essentially that it has these properties, but we're going to take a look at them later on in greater detail. We'll do a programming example for them and so forth. But under the hood, the way it's managed is as a tree. So then what is a tree? A tree, you can think of it, we talk about it having a root or whatever, but you can also think of it as like having a Christmas tree appearance as well, where there's this single point at the top and then it spreads out as it gets further, right? The terminology is kind of a reverse tree, but I think a family tree is also an appropriate representation of kind of how it is viewed as well, right? So family trees can go either up or down, right? So if you are a 90-year-old individual and you've had your time, you've had a bunch of children, they've had a bunch of children, and so forth, then you can view your family tree as being your progeny, the descendants of you, and so you can see it kind of spreading out, and so you are the root of that tree. You can also go in the other direction and look up your ancestry, and so your parents had their parents, and their parents had their parents, and so forth. But in that case, you are also the root of this structure that is going up. Another example of trees is the business structures. Corporate structures have tree models, right? So everyone sort of reports to the CEO and in some form or fashion, right? So all of the other executives are accountable to this individual. Uh, you know, ignoring the board of directors and the owner, whatever, right? And then you know, each of those executives will have their directors or VPs or whatever that report to them. Those people in middle management will have other managers who actually work directly with the individual contributors and so forth. And so that follows a tree structure as well. Okay. Graphs and lattices. All right. So this is a lattice is a special type of a graph. It has this concept of height in a sense, whereas a graph is a little more freeform. But in both cases, there are just multiple connections. So in a tree, there's only one way to get from point A to point B. Right? So there's only one path that connects you to your grandmother on your father's side, and that's to go from you to your father to your grandmother. Right? And so a graph is honestly, if you go back far enough in your family tree, a graph is probably more appropriate, where, you know, like 15, 20 generations back, you know, some of your lines start to connect or whatever, so that your 8 times great grandfather appears on both your mother's side and your father's side, right? So that it creates these multiple ways to get to a single point. It's yeah. But trees are definitely the appropriate local representation of this family lineage, whatever. Another thing that can be represented using graphs is the interstate highway system. If you're going from Dallas to New York City, you can go along the south and then up the east coast. You can go straight up 35 and then along the north to it, or you can kind of cut across. Right? You can take these highways that kind of run diagonally, or there's several options. You don't have to commit to any one path, and so everything is has this several ways to get there. Right? There's many ways to shear that sheet. So graphs, just like trees and heaps and everything else, are composed of nodes and edges. But again, the distinction between a graph and a tree is that a tree has this restriction that there is only one way to get from node A to node B, and graphs are in many ways. And so there's a lot of algorithms that we'll discuss in terms of what is a best way, or how to identify something you might call a best way to get from A to B on a graph. Whereas a tree, there's really only the one way. And then because it's composed of nodes and edges, a tree is actually just a graph. It's just with an additional restriction, or an additional assumption that is guaranteed by the data type. And then lattices, they show up in group theory, which is more on the math side of things. We'll get to that when we get to it. All right, so enough about data structures. So now we're on to operating systems. Right? So it's hard to talk about operating systems without talking about the physical computer itself first. Right? So what are the components of the computer, and then how does the operating system use that, and then how does whatever programs we write fit in within the framework of the operating system. Okay, so the computer, the heart of the computer, the brain of the computer is the processor, and so if you open up your computer and you take a look, you'll see that there's this main board, this main circuit board. It's commonly called the motherboard. Some people just call it the main board. And the CPU sits there, and even if there's multiple CPUs, they're all fixed on the main board. And then the modern desktop computer will allow for these expansions, and even the laptops as well have these expansion slots in their boards, so you can kind of customize the laptops. And so there's the processor, and then there's these fixed locations where these sticks of memory slide in, and then there's all sorts of properties that are, optimizations that may have been made on the motherboard, such as like dual channel memory and so forth. And so you're trying to send this this electrical current through this circuit, and you want to make sure that you're taking it, or if you want the best, right, that you're that everything has its chance to run into as little interference as possible. And so it's possible to that's where dual channel memory comes in. But again, that's probably a little more nitpicky than I wanted to get into. Anyway, so the memory is connected to the CPU so that it can pass data back and forth based on whatever program is being executed. So the program has its own memory associated to it, and then whenever it's active, it'll be copied. Certain data will be, and routines will be copied into the registers of the CPU, and that's the cache, the L1 or the L2 cache or whatever, and then the CPU has these gates or whatever, these logic gates or whatever, that will perform the actual computations necessary based on whatever instructions they receive. And so the every action, load from memory, copy to this register, perform this operation on these two registers, return, blah, blah, blah. Every one of those instructions happens with a cycle. There's like this metronome on the CPU, and it tells it when it's time to go to the next step, right? So it should have taken you one cycle to do this. Go to the next thing. Go to the next instruction. Go to the next instruction. And so that is what the gigahertz in your CPU represents. It's the pacing of that metronome. And then if you have a multi-core CPU, then there's still just the one metronome, but now you have more logic gates. You have essentially double the number of logic gates. The onboard, or the on-die cache, the L2 cache or whatever, it's shared between these two processing units. Whenever it's a single CPU with multiple cores, right? It's all shared, but the throughput is faster because you just have more avenues for crunching stuff, right? for iterating through these instructions. Okay, so we'll talk a little bit about the role of the operating system in pausing the action in one program and then loading another one in. So in terms of scheduling and so forth, so that's the CPU and memory, and then the disk drives. So whether it's solid state or rotating disk, spinning disk, or external disks, or whatever, they will connect to the main board as well. So there will be a cable that physically connects them, and then so the logical grouping, or the electrical grouping of these, if you will, are connected of these points on your computer, these physical points, they're connected through bridges and hubs, which are just these. You can think of them as these nerve coils or whatever, analogous to the way the spine carries signals up and down the body. And so, in the way that we have our arms and our legs and our head, and we have our heart as well. We have our torso, which is our upper body, and our legs, which is our lower body, and the computer has a similar division. So there's a north bridge and a south bridge. And so the idea is that the things that are necessary for the computer to perform its role of running an operating system which executes programs is all going to be grouped on the north bridge. And then inputs, device inputs, and things that you connect through USB and so forth, that'll all come in from the south bridge. And so the separation is that everything that's on the north bridge is kind of automatic. So the communication between the CPU and the memory sticks is very, very rapid. Hundreds of megabytes per second sent back and forth over those channels. But like if you type at like 120 words per minute, that's really fast, and that's still less than a kilobyte per minute, right? So it's not the 500 million bytes per second that is happening on the north bridge. And so to sort of deal with the fact that data flows in at a typically slower rate, these slower input devices will be put in a separate bridge, and then it'll sync in, causing these interrupts or whatever as needed, but coming in from the south bridge. But some of that has been modified more recently. So when I built my first computer, the graphics card was still connected through the south bridge, but now the graphics card is sending just as much data back and forth to the memory and the CPU. The channels of communication are just as fast, that they've moved that into the north bridge because it's just faster communication, and it's just dealing with more and more data. So it kind of deserved that promotion. With the advent of solid state drives, external hard drives have become much faster as well, so that now I think USB 3 connects directly to that faster bridge as well, so it doesn't have to go in through the south bridge. I believe that I may be mistaken. USB 3 may actually go in through the south bridge, but anyway. And so there's all of these different considerations in, what is the best way to structure the hardware so as to support the operating system and allow it to take advantage of faster and faster processes. And so that was one of the optimizations that was made. You have all of these peripherals. You have things like, you used to have a separate sound card, but now that tends to be on the motherboard as well. And so a lot of the stuff that's common is now being built directly into that main board. And it helps in terms with airflow and keeping the processor cool and keeping everything cool, to not have a bunch of cards that are getting in the way, these expansion cards that are slowing things down. And so for the most part, you can have a pretty nice computer with just hard drives, the main board, the CPU, the memory, and then a graphics card. And then obviously you need your monitor or monitors, and your keyboard and mouse and so forth. But you used to have to plug all that in separately. The network card or the modem or whatever used to go into the expansion slot. So that's the hardware side of things. So then what does the operating system do? Okay, well, the operating system is a juggler. It is a premium level juggler, where you know it deals with all of these this incoming data, so these interrupts that we had discussed, or these events such as keyboard input, mouse movement is also an interrupt. It deals with input coming from streaming devices like a speaker, or sorry, a microphone, or a webcam, or whatever else. It identifies, hardware, plug and play hardware that you stick in with your USB or whatever, which is just another form of interrupt, but now it's a hardware, or I guess it's all hardware interrupts. But and then it has these ongoing programs that it manages, and if you go to your task manager if you're on Windows, or if you get a process listing if you're on Linux or Mac, you'll see that there's more processes running than you have CPUs on your machine. So how is that possible? How are they all running simultaneously if everything eventually filters down to just this very small set of logic gates that are actually performing all of the processing? It's a juggling act. So the operating system, what I would argue is the main feature of an operating system, is its ability to time slice. So it says, okay, well, you're going to get, maybe 50 million clock cycles, and then I'm going to swap you out for something else. And in doing so, everything gets its slice of time, almost every second, every few seconds. And that tends to be enough to keep things running smoothly. Since most of the time things are very passive. Like if you think about your web browser or whatever, you may feel like you're going through it really quickly, but in terms of the billions of operations per second that your processor is doing, you're basically always standing still, even when you're very active on it. So the scheduler, the thing that says who gets CPU time when, is really the main feature of the operating system. But as programmers, it has this additional role of resource allocation. So it juggles us in and out, and then whenever we're actually running, we politely ask for new blocks of memory. And so it'll go into what is effectively a warehouse, right? It's this if we go back to the locker analogy, it's this enormous array of lockers. So if you have 8 gigabytes of memory, then if you think of each locker as having a kilobyte of memory, then you have 8 million lockers to work with, 8 million 1 kilobyte blocks to work with in your 8 gigabytes of memory. And so while our program is running, we can ask the operating system to set aside a few of those lockers for us, and then we tell it how much we need, and then it'll either it'll set aside that block of memory, or it'll tell us that it has no memory to give, or that we've used more than we should have. Right? And both of these manifest as an out of memory exception. So whenever it creates it passes back. So it creates the memory, and then it passes us back a pointer to that new block of memory. And then we discuss scheduling, right? So the juggling act of making sure that every program gets a chance. And because, if you think about all of the programs that you have running at the same time, you can't just wait for a program to finish in order to feed in the next one. You have to pause it and move it out of the processor and load in the new active routines for some other program. So it's just because these things never end, right? You're not guaranteed that a particular program is going to terminate. I leave my web browser open all the time. I leave Python interpreter instances open all the time. And so if the operating system waited for these to terminate before allowing something else processor time, then the computing experience would be not a very pleasant one, right? So it has to perform this juggling act, and so the scheduling is one of those main features. And so what happens when it doesn't go well, when something happens, right? Well, there's two instances. There's starvation and there's thrashing. So Linux and Unix and Mac all have these concepts of niceness for processes. And essentially things like a database can be configured to have very little niceness. And that is essentially how greedy they want to be with their scheduling time. So it's like walking into a grocery store, right, and just always bumping your way to the front of the line. Like, look, I'm getting food for the president, right? Like, this is more important than whatever you're doing. And so that's fine because you're the one configuring it. So if you say that it needs it, then that's fine. But if the operating system honors that, then there are other programs which will be starved of time. They just won't get their slice of time because the database is always working. It's it has maybe it's poorly normalized, or maybe it's just got too much data or whatever, and so it's just taking forever to return. And so you have this application that's not responding. I'm scrolling, I'm typing, and it's not responding. Well, your program, the one that you're interacting with, is being starved for processing time. And so that can happen if certain things are given priority and other processes suffer. Another extreme instance of when things go bad is thrashing. So I told you that the scheduler is a juggler, and so it tries to make sure everything gets something like a fair slice of time with the processor. So what happens if instead of 100 processes, we go to 1,000 processes, or we go to 10,000 processes, or 100,000 processes? Well, the operating system isn't going to stop trying to juggle, and it's able to perform a couple billion actions per second. So it thinks, well, okay, 100,000 processes, whatever, I can still do that. I can perform over 1 billion actions per second. And so it creates this fair slice, right, so that everything gets 20,000 cycles or something like that. But it has to make sure that it leaves room to pause whatever is executing, to move the current state of that program out of the processor's cache and into the random access memory, into the RAM or the memory, to copy in the routines from the last pause point of whatever program is next, and then allow it to go. Well, that takes maybe 1,000 clock cycles, maybe a couple thousand clock cycles, and so that eats into that slice of time that was allocated. And so you get to this point where you have so many processes that are running that the operating system is in trying to give everything a fair slice of time, because it doesn't know which processes actually have a chance of finishing. It spends all of its time moving things in and out of memory, and so it's not starving these processes, but they're not getting anywhere, because even though they're getting clock cycles, the operating system is just really eating into those clock cycles, loading programs in and out of memory. And really, once you get to that point, you're probably out of true memory, and you're relying on something called virtual memory, where you start to borrow some space from the hard drive, and you treat that like additional memory storage. Well, whenever you do that, and something that I noted up above, it gets slower. So I'd mentioned that these peripherals that are coming in through the south bridge, like the hard drive, typically, unless you have a solid state drive and a dedicated channel which passes through the north bridge. Certain things have gotten so fast that now they're connected directly to the north bridge. So unless you have one of these exceptional cases, then you're going in through the slow path whenever you access this. So it's slower than the memory access that you're using, which is right next to the processor on the north bridge. And so now you're waiting even longer to use this additional storage space that you've borrowed from the hard drive. And so just a guiding rule whenever you're talking about waiting longer. So if something takes X amount of time to load from the processor cache into the logic gates and perform the number crunching and so forth, then it'll take 10 times that in order to get it from memory into the processor and into the logic gates. And it'll take 100 times the original amount if you're doing it from the virtual memory instead of there. And then, so if you're not dealing with your hard drive's cache, then it'll probably take an additional factor of 10 times if you're dealing with the spinning disk to locate the right sector and set the head and then read it and then copy it into the hard drive cache, or to write it out back through the south bridge up to the north bridge into the appropriate location in memory, and then from the memory into the hard drive or into the processor and so forth, right? So now you're looking at a factor of 1,000 of what it was whenever it was just on the processor. And then it's even slower if you're reading from an optical drive like a DVD or a CD or Blu-ray disc, because those discs, while they're spinning pretty quickly, they're not spinning at the same speed as this fixed enclosure of a spinning hard drive disk. So now you're looking at something that takes 1,000 or 10,000 times what it did whenever it was on the processor's cache. And so it gets slower and slower, and then if you're talking about reading from a tape drive or whatever, then it's that probably is an additional factor of 100 or 1,000 on top of what you had whenever it was a Blu-ray disc. And so there are these orders of magnitude in terms of performance degradation, and the subtle art of software development is kind of understanding where if you just get a little bit too lazy in terms of how much resources you're consuming, that even if your algorithms are good, the amount of memory and space that your footprint is taking up in order to execute your program, that can itself start to slow it down, and it's related to the way the hardware is structured and how all of that interacts. And then the operating system itself, if you're running too many processes, thrashing will definitely affect it as well, right? So there's a lot of different places to look. Well, we didn't get a chance to talk about file systems. I'll wrap up this overview next time, and then we'll dive into something else. Okay, well, have a good weekend, and we'll meet again next Tuesday.